In this video, I'm going to start with a review of titrations and titration curves, and then we're going to go into some calculations based on titrations. So a titration is a procedure where a known reagent solution called the titrant, so for example the sodium hydroxide in the KHP experiment, is added to an unknown analyte until the reaction is complete. And because we know the concentration of the titrant, we can use the stoichiometry of the reaction to determine the unknown concentration. So in any titration, whether it's acid-base or complexometric or redox, we will be adding the titrant until the analyte is used up. And we need to know when that happens. So something has to change in the solution in order for us to know when that reaction is complete. So it could be the change in color of an indicator, it could be the change in voltage between electrodes, or it could be something like the presence of a precipitate. But something has to change in order for us to know when the reaction is complete. So when the reaction is complete, we talk about two different points. We talk about the equivalence point and the end point. And there is a difference between them. So the equivalence point is when the quantity of titrant added is stoichiometrically exact in comparison with the analyte. Now this is something we can never get to because we can never add just enough moles of the titrant to react with the moles of analyte that are present in a mixture. So the end point is what we see instead of the equivalence point, where something about the solution changes. Again, the color, a formation of a precipitate, or the change in a voltage, for example. And the end point is usually really close to the equivalence point. And if we're using an indicator, as we'll see a little bit later, we have to make sure that we choose the indicator correctly so that it changes color near the equivalence point. We can't just choose any indicator, it has to be the right one. So while doing a titration, and especially when using an indicator, you will run into something called titration error, and that is the difference between the endpoint and the equivalence point. So remember, the endpoint is what we observe, something that is close to the equivalence point, but not exactly at the equivalence point. So is this titration error a random error or a systematic error? So remember that a systematic error is something that we can find and correct, whereas a random error is something that we can't find and we would have to use statistics in order to take into account those types of errors. So it turns out that a titration error is a systematic error. It's something we can find and fix. So if we were to take a solution without the analyte and add the indicator to it, you have to think about what's happening during a titration to that indicator. If the indicator, for example, is phenolphthalein, and we start with an acidic solution, as we're adding base to it, eventually the indicator turns pink. Now why does it turn pink? Well, it's turning from its acidic form, which is colorless, to its basic form, which is pink. So you're actually titrating the indicator as well as the analyte. So that's the reason that when you put indicator into your solution, you don't put in very much. You only put in a few drops. So to do a blank titration, you would take a solution without the analyte, add some indicator, and see how much of the titrant would need to be added to change the indicator from, say, colorless to pink. And that volume is going to be your titration error. So once you know the volume of titrant needed to titrate the blank solution, then you could subtract that volume when doing a titration with your analyte. And that will give you a more accurate volume for the end point of that reaction. So pictured here are two acid-base titration curves. The one on the left, the analyte is an acid, and we're adding base to that analyte, whereas on the right, we start with base as the analyte and our titrant is an acid. Now, it doesn't matter if the titration is an acid-base titration, a complexation titration, a redox titration, or any other type of titration. The shape of the titration curve is going to be the same. What would change is the labels on the axis. If you're not adding acid or base, then you're not going to be monitoring pH. You'll be monitoring something else, maybe voltage. And the volume of titrant is still going to be on the x-axis, but it wouldn't be an acid or a base. It might be EDTA, for example, when you're doing the copper EDTA titration, or it could be the volume of dichromate, for example, in a redox titration. So again, here's just a couple different titration curves again, and these ones are showing the different labels on both the y-axis. So for example, PCD is essentially like pH in a way. So pH means the negative log of the concentration of H+, whereas PCD means the negative log of the concentration of cadmium. In the middle one we have voltage, and on the one to the right we have the negative log of the concentration of silver. And on the x-axis we have volume of EDTA, volume of cerium, or volume of silver nitrate. So you don't have to use concentration to monitor a titration. You can use absorbance, temperature, mass of precipitate, voltage, or any other useful property of that solution. So I'm going to spend the rest of this chapter talking about acid-base titrations. So we're going to start with the titration of a strong acid with a strong base. We're going to practice building that titration curve, which is a plot of the pH versus the volume of the titrant added. And we're going to be going over the steps that are involved in determining the pH at different points on the titration curve. So the first step in this process is to write out the reaction between the analyte and the titrant. And for a strong acid, strong base titration curve, all we care about is the concentration of H+ and the concentration of OH-, and we know the reaction between a strong acid and a strong base results in the production of water. So if the base, the OH- is our analyte, we're going to be adding H+. So any amount of acid or H+ that we add to this reaction is going to react completely with the base that's in solution. So if we add 1 mole of H+, it's going to react with 1 mole of OH-. So what we're going to be doing is determining the pH at different points on the titration curve. And one of these steps, we're going to have to determine where that equivalence point is. So how much titrant would we have to add in this particular situation, listed right here, to get to the end point. So we're going to talk about 3 different regions of the titration curve. We're going to talk about what happens before the equivalence point. And before the equivalence point, the pH is determined by excess analyte because we haven't yet added enough of the titrant to react with all of the analyte, because we haven't yet added enough titrant to react with all the analyte present in our solution. So in our example, the analyte is OH-. We're going to look at the equivalence point. So this is when the amount of H+ that is added is just enough to react with all of the analyte. So what is the pH of this going to be? And after the equivalence point, the pH is determined by excess titrant. So in this case, it's going to be determined by excess H+. So remember, the pH at the equivalence point for any strong acid, strong base titration is 7. And it's only 7 for strong acid, strong base titration curves. Okay, so this is never true for weak acids and bases. So at the top of this graph, it shows you that before the equivalence point, we are only worried about the amount of excess OH-, and that's going to be determining what the pH is, whereas after the equivalence point, all we care about is how much excess H+ there is, and that's going to be determining what the pH is. And of course, the pH at the equivalence point is going to be 7. So let's just go through this practice question. So a titration of 50 milliliters of 0.02 molar potassium hydroxide with 0.1 molar HBr. So potassium hydroxide is the analyte. That's the compound that's in the Erlenmeyer flask. And HBr is the titrant. That's going in the burette. So we'll look at 3 different points on this titration curve. Before the equivalence point, after we've added 3 milliliters of HBr, at the equivalence point, and after the equivalence point once we've added 10.5 milliliters of HBr. So to save a bit of time and keep this video a little bit shorter than it would be otherwise, I've already worked out these problems, but I will go through each of the steps and explain what's going on. So the first thing I have done at the top is to determine what the pH of the solution would be before any HBr has been added. So this is if we just have a solution of 0.02 molar potassium hydroxide. Now, hopefully you remember how to do this. If you don't, what you have to do quite simply is to calculate first pOH, so the negative log of the concentration of the strong base, and then you can turn pOH into pH by subtracting the pOH from 14. Okay, and that ends up being a value of 12.3. So now that we know the starting point, we know that any other pH that we calculate has to be less than 12.3. Because once we start the titration, we've started to add acid, and that's going to react with some of the OH minus, which will then make the pH more acidic. So we're going to look at a point before the equivalence point when 3 milliliters of HBr has been added. So the first thing that we need to do is know how many moles of OH minus were initially present in the solution. So before anything was added, how many moles of OH minus are there? So we simply take the concentration of the KOH, multiply it by the volume of the solution, which is 50 milliliters, and then we end up with 1 millimole. Okay, so I'm doing it as millimoles just because it makes it a little bit easier rather than writing out 1 times 10 to the minus 3 moles. Okay, so we're right there. So we have 1 millimole of OH minus initially present. Now we've added 3 milliliters of HBr. So now how many moles of HBr, or H+, have we added to the solution? Well, we know the concentration of HBr, 0.1 molar. We know the volume. So we do the same calculation that we just did in step 1, and we end up with 0.3 millimoles of HBr, or H+, that has been added to the solution. Now, since the H+ will react completely with the OH-, the next step is to simply subtract the moles of H+ from the moles of OH- initially present. So if we do that, we have 0.7 millimoles of OH- remaining. And now in order to figure out what a pH is, we're going to need to find concentrations of H+. But we don't really have H+ right now, we have OH-. So we can first find the concentration of OH-. We just calculated the number of millimoles of OH-. And the volume is going to be the total volume of the solution. So we started out with 50 milliliters. We added 3 milliliters of HBr. So the total volume is now 53 milliliters. So to figure out the concentration of OH-, you just take the millimoles divided by the milliliters, and we end up with 0.0132 molar. Now there's a couple different ways you can use to find the pH. I chose this way, so I first found the pOH, take the negative log of the concentration of OH- to get a pOH of 1.879, and then the pH is just going to be 14 minus 1.89, and that's going to give us a pH of 12.12. So that makes some sense. Remember, initially we had a pH of 12.3. Now we have a pH of 12.12. So the pH has decreased a little bit because we've added a little bit of acid. So for a strong acid, strong base titration curve, we don't have to do any calculations for the second part to find the pH at the equivalence point, because we know already that the pH is going to be 7. We'll actually be finding the volume at the equivalence point in the next step, because we'll have to know how much excess H+ has been added. So the one thing I do want to emphasize about the equivalence point is that we have this reaction here. The reason that this is pH 7 at the equivalence point is, for example, we started with 1 millimole of OH-. To get to the equivalence point, we would have to add 1 millimole of H+. So the H+ and the OH- would cancel each other out. So the only thing we have left in that solution at the end point, or more specifically at the equivalence point, is water, and the pH of pure water is 7. So now let's talk about after the equivalence point, when 10.5 milliliters of HBr has been added. So the first thing we have to do is find the volume at the equivalence point, because we need to know how much excess HBr has been added beyond the equivalence point. So we know at the equivalence point, the moles of OH- that were present initially have to be the same as the moles of H+ that were added to the solution. So in order to figure out moles of OH-, we have the concentration of OH-, we have the initial volume of OH-, so that can give us the moles. And we do the same calculation for the acid. We have the molarity of the acid But we don't have the volume yet because that's what we're trying to figure out, right? We're trying to figure out how much acid needs to be added to get to the equivalence point. So we're going to solve this equation for the volume of acid. So the molarity of the base times the volume of the base divided by the molarity of the acid, and that gives us an equivalence point of 10 milliliters. So the next step is to find the excess number of moles of H plus that have been added. So we know 10 milliliters of acid gets us to the equivalence point, and another half a milliliter is excess. So we can determine the moles of excess by taking that volume and multiplying it by the concentration of the acid, and that gives us half a millimole. Now that we know the moles of the acid that are in excess, we need to know the concentration because that's going to allow us to determine the pH. So the concentration is going to be the millimoles of acid divided by the total volume. So we started off with 50 milliliters, 10.5 milliliters of acid was added, so our total volume is 60.5 milliliters, and we end up with 0.00826 molar. And now to determine the pH, we just take the negative log of that concentration, and we get a pH of 2.08. So now let's switch over to weak acid and weak base titrations. So in this particular example, I'm showing the titration of a weak acid with a strong base. Now the titrant in any titration or any acid-base titration is going to be either a strong acid or a strong base. There cannot be a weak acid or a weak base used for the titrant. Okay, so the burette itself is always going to have a strong acid or a strong base in it. The flask can be either a strong acid or base or a weak acid or base. So for a weak acid, strong base titration curve, the equivalence point is never going to be 7. And it's never going to be 7 for a weak base, strong acid titration curve either. So there are a few areas that I want to point out on this titration curve. The first is just the general shape. So if you compare this titration curve with a strong acid, strong base titration curve, you notice initially there is a bit of a steep portion of this curve, but then it flattens out a bit. Whereas on a strong acid, strong base titration curve, it's fairly flat the whole way up until, somewhere around here. Okay, so that's one difference. The second difference is since you have, in this case, a weak acid and you're adding a strong base, the reaction of the strong base with the weak acid is going to be converting some of the weak acid to its conjugate base. So upon addition of strong base, and in this region right here, well, pretty much the region after any addition of strong base, we have what is called the buffer region because we formed a buffer. The strong base has converted some of the weak acid into its conjugate base, and when we have both conjugate base and weak acid in solution, then that means we have a buffer. So because we have a buffer, there's also an area on that curve in which the pH of the solution is going to equal the pKa of the buffer. And if you remember from the previous discussion, the previous section, we talked about what conditions are needed in order for the pH to equal the pKa. And remember that was when the concentration of the weak acid is the same as the concentration of the weak base in solution. So this point right here is going to be the midpoint of the titration. So halfway between the starting and the end point of the titration. So when half the volume to get to the equivalence point has been added. And then in this case here, we have the equivalence point being above 7. And then after the equivalence point, the shape of the titration curve is exactly the same as a strong acid, strong base titration curve. So to do these calculations, we have to bring in everything we know about acid-base chemistry and pH. So we should write out the titration reaction, make sure it's balanced. Remember that strong and weak acids and bases react completely, and we'll need to calculate the volume of titrant needed to reach the equivalence point because each part of the titration curve that we talk about now is going to require a different type of calculation. And if we don't know where we are on the titration curve with respect to the equivalence point, then we don't know what kind of calculation we have to do to determine the pH. So we're going to talk about 4 regions of this titration curve. First, before any base is added, before any titrant is added. So we have just a solution of acid in water, and we're going to solve the pH as usual for a weak acid solution. The second part we're going to look at is from the first drop of base to just before the equivalence point. So this is the buffering region, and we're going to be using the Henderson-Hasselbalch equation to determine the pH. At the equivalence point, all the weak acid has been used up to form its conjugate base. So now we have a weak base problem. And after the equivalence point, we're going to be worried about excess titrant, excess base in this case, and we're going to solve for pH just the same way as we did in the strong acid, strong base example, where we just try and figure out how much excess base there is. So we're going to use this example, titrating 50 milliliters of 0.02 molar MES with 0.1 molar sodium hydroxide. We're going to find the initial pH before any sodium hydroxide has been added, after 3 milliliters of sodium hydroxide has been added, at the equivalence point, and after 10.2 milliliters of sodium hydroxide has been added, and that will be after the equivalence point. So for the initial pH, this is just a simple weak acid problem. So ones that you've done before, so I'm not going to spend a lot of time on this. So you can set up a nice table. We have an initial concentration of the acid. We know we're going to lose some of the acid. We're going to gain some of its conjugate base and H+, and our final concentrations or equilibrium concentrations are going to be labeled as such. And to determine the pH, we'll write out the equilibrium constant, the Ka expression, substitute in the equilibrium concentrations from this line here, and then solve for x to find the pH. So after doing the calculation, you'll find out the pH equals 3.98. So this is the initial pH before any sodium hydroxide has been added. So now we're going to talk about how to determine the pH before the equivalence point. So the first thing we should do is to determine for sure if we are before the equivalence point. So on a homework or a worksheet or an exam, you won't be given the information that says you are before the equivalence point. So you need to know where you are on the titration curve. So we find the volume of the equivalence point, and then that'll tell us that, okay, yeah, we're before the equivalence point. And then we can recognize that before the equivalence point of a weak acid, strong base titration curve, we formed a buffer. So we can use the Henderson-Hasselbalch equation to determine the pH. So we'll need to determine moles of MES, which in this case is our weak acid. We'll need to determine how many moles of sodium hydroxide were added, and we'll need to determine how many moles of MES are remaining after the reaction, and how many moles of the conjugate base A- have been formed. And then using those numbers, we can plug them into the Henderson-Hasselbalch equation to determine the pH. So let's just quickly go through the solution. I'm going to call the MES HA because it's just a weak acid. It makes it a little bit easier to follow. So first we're going to find the volume at the equivalence point, and this is the same calculation that we did in the strong acid, strong base titration curve. So the numbers are also the same, so I'm not going to go over again how to do it. If you need to know how to do the calculations again, just look back in the video. So find the volume at the equivalence point, 10 milliliters. Find the moles of HA initially present. Okay, we did this before already. We have the concentration of HA, we have the volume of HA, so we have 1 millimole of HA initially, and find the moles of OH- added after adding 3 milliliters of sodium hydroxide with a concentration of 0.1 molar. That ends up being 0.3 millimoles of OH- added. So now realize that the moles of OH- that have been added, those are reacting with the HA and converting the HA into the conjugate base A-. So we have 0.3 millimoles of A- that have been formed, and we need to find the moles of HA that are remaining. So that's simple again. We take the initial moles that we started with, we subtract the moles that have been converted to A-. We end up with 0.7 millimoles. And now we have enough information to determine the pH. So we're going to use the Henderson-Hasselbalch equation, which is pH equals pKa plus log of A- over HA. The pKa is given in the question as 6.27. And we just make sure that we do the ratio correctly. We have log of the moles of base divided by log of the moles of acid. Remember again, it doesn't matter what the total volume is, because if we're dividing each of these numbers by the total volume, which in this case will be 53, that ratio within the parentheses is not going to change whether we divide by 53 or not. So we can just use the moles. So we solve for this, we end up with a pH of 5.9. So we expect the pH to be a little bit higher, right? We were adding base. Initially the pH without any added base was 3.98. Now it's higher, pH 5.9. So now we're going to find the pH at the equivalence point. So remember, this is not at pH 7 because it's not strong acid, strong base. It's weak acid, strong base. So first we need to find the equivalence point volume, which we already did. We know it's 10 milliliters. And the volume of the solution is going to be important here. So it wasn't important when using the Henderson-Hasselbalch equation, but it will be important at the equivalence point. So what do you predict the pH will be? Do you predict it to be greater than 7 or less than 7? Right? You know it's not going to be 7. So how can we do that prediction? So if we write out the reaction that we have initially, so we have HA plus OH minus, and that's going to produce A minus plus H2O. Now what happens when we've added enough OH minus to react with all the HA? So we know we have 1 millimole of this, of HA. So if we added 1 millimole of OH minus, what's going to happen? Well, all of the OH minus is going to react with all of the HA, and we're going to be left with 1 millimole of A minus, right? Because the OH minus has converted the HA to its conjugate base. So now what do we have? Well, now we have a reaction of A minus plus H2O. We have a weak base in solution now, so that's going to make HA plus OH minus. So at the equivalence point of this particular titration, we're adding base, we're turning weak acid into its conjugate weak base. So at the equivalence point, the only thing remaining in solution is the weak base, and since it's a weak base, it's going to react with water and produce a basic solution. So you should expect the pH in this situation to be above 7. Now, if we had the opposite situation where we had a weak base reacting it with a strong acid, that strong acid would react with the weak base, turning that weak base into its conjugate acid. So at the equivalence point, the only thing remaining in solution would be the weak acid. So in that case, the pH would be less than 7. So let's just quickly go over this calculation. So at the equivalence point, all of the HA has reacted with OH minus, and there is no original HA remaining, so only A minus is left to react with water, which is just what I showed on the previous slide. So now we have a weak base problem. So we need to figure out how many moles of A minus have been created, okay, and that's going to equal the moles of OH minus that have been added, right, because all the OH minus has converted the HA into A minus. So the number of moles of OH minus is equal to the number of moles of A minus created. So we're going to have 1 millimole of A minus. And the total volume of the solution now is going to be important. We already determined that the equivalence point is at 10 milliliters. Initially we started with 50, so 50 plus 10, we got 60 milliliters as our total volume. Since this is a weak base problem, we're going to have to go through the equilibrium expression or an ice table if you want to do it that way. So we're going to need concentrations. So the concentration of A minus is going to be the moles per liter or the millimoles per milliliter, which gives us 0.01667 molar. So now the next step, if you want, you can make an ice table. Okay, so here's our reaction, and this is the concentration of A minus. And initially we had 0 HA and 0 OH minus. Once it reaches equilibrium, we're going to have the situation here at the bottom of the ice table. So now since we're dealing with a base, we have to find Kb. Right? Now we're given Ka in the question as 6.27, so we have to convert that into a Kb. So when we do this calculation, we get a Kb of 1.86 times 10 to the minus 8, and now we can use the equilibrium expression to determine the concentration of OH minus in this solution. So Kb equals the concentration of HA times the concentration of OH minus divided by the concentration of A minus, which ends up being x squared over the concentration of A minus minus x. But if you remember, we can ignore this x in the denominator because our Kb value is really small, and the value for x is not going to change the concentration of A minus in this case. If we subtract x from 0.01667, we're essentially going to end up with 0.01667 again. So if we solve for x, we end up with 1.7 times 10 to the minus 5 molar, which is the concentration of OH minus. And then now we have to turn OH minus into H plus, so we can figure out the pH, or we can find POH, as I've done here, as 4.75, so negative log of the concentration of OH minus, and then turning POH into a pH through this equation here, and we end up with a pH of 9.25. Okay, so again, this makes some sense. We started with an initial pH of 3.98, and then our next step, we had a pH of a little bit over 5, and now at our equivalence point, we have a pH of 9.25. We know the pH has to be greater than 7 because that's what we predicted based on the reactions that are happening during this titration, so this makes some sense. Now, after the equivalence point, we have the same calculation that we had when we were dealing with a strong acid, strong base titration. We need to find the excess moles of OH minus added, find the concentration of OH minus from that excess number of moles, and then find the pH. Okay, so we already know that the volume at the equivalence point is 10 milliliters. And what we have to do is to find the excess number of moles of OH minus that have been added. And we know it's 0.2 milliliters. So to determine the excess moles, we take the 0.2 milliliters multiplied by the concentration of sodium hydroxide, and we end up with 0.2 millimoles of excess OH minus. The total volume is going to be important because we're going to need a concentration of H plus eventually. So the volume is going to be 50 plus the 10.2. So our volume is 60.2 milliliters. Concentration of OH minus is going to be the moles of OH minus divided by the total volume. So we have 0.00332 molar. And then to determine the pH, again, I did POH first. So POH, negative log of the concentration of OH minus, 2.48, and then 14 minus 2.48 to get to the pH of the solution, which is 11.52. So again, makes sense because it should be higher than the previous pH, which was about 9.5. Now we've added even more base, so we should have an even higher pH. So here's another example that you can try. I'm not going to go over the calculations myself, but I have given you the answers, so if you want to try it yourself, you can. The process is similar to the process that we've just gone over. The only difference is in this case, it's a weak base, strong acid titration curve, whereas in the example that I worked out, it was a weak acid, strong base titration curve. So finding the endpoint in a titration is the most important thing because that gives us the information we need to determine the concentration of the analyte. And the endpoint is determined by an abrupt change in a physical property such as pH or color. So you have to choose an indicator that changes color in the range where the pH changes most. So different indicators change color at different pH values, and the transition range of that indicator should overlap the steepest part of the titration curve. So you want the indicator to change near the equivalence point, not somewhere else. And if you choose an incorrect indicator, you're going to add to the titration error. So I've already answered the question, what if we add too many drops of indicator instead of just a few? Would there be any error? Of course the answer is yes, because again, you're titrating the indicator as well as the analyte. So it would take a little bit more titrant in order to make that indicator change color. So you would have passed the endpoint a little bit if you add too much indicator. So in the titration curve to the right, it shows two potential indicators that could be used for this titration. So in this case, the endpoint is around a pH of 5.5. So you want an indicator that changes color at around pH 5.5. So in this case, you could use bromocrestal purple, which changes color over a range of between pH 7 and 5, or bromocrestal green, which changes color over a range of pHs between about 6 and 4. So if the endpoint of this titration is right here, so that looks like it's about pH 5.5, both of those indicators change color near that region. Okay, so both would be useful, And maybe the bromocrestal purple will be a bit better since there's a little bit more overlap with that color change and the equivalence point. Another way to do this would be not to use an indicator, but to use some math instead. So you get a little bit of practice doing this with the iron bidichromate titration. So instead of using an indicator, if you just monitor the pH using a pH probe, you get a titration curve that might look something like this. Now this particular titration curve has two endpoints, so two steep portions of the curve. So what you can do is do some math and take the first derivative and the second derivative of the titration curve. So remember, a derivative measures the change in slope of the graph. So as the pH is increasing, the slope of the curve is increasing. And then as it reaches the top of the first derivative curve, we've reached a point on the titration curve where the slope is changing from a positive slope to a negative slope. So then we have the first derivative curve decreasing, and then again it increases to a point where it changes slope again from positive to negative, and then decreases as the slope changes. Okay, so in this case it's showing two different endpoints. To be a little bit more accurate, you can use a second derivative, which is monitoring the slope of the first derivative curve. So how does the slope of the first derivative curve change? So again, it starts off slowly increasing. It gets to a point where it's at its highest increase, and then where it crosses the x-axis is right at the tip, or the very peak of that curve there. So where the slope is 0. Right? So the curve is going from a positive slope to a negative slope. It's got to pass through 0. So that right there is going to be your endpoints for the titration curve. So it's a little bit more accurate because it's very unlikely that you'll have a point that sits right on that endpoint. So you can look at this curve and zoom up on it and determine where the endpoint is. Okay, so I know this was a long video, but that's all I have. If you have any questions, please let me know.